Good afternoon. I'm Dick Sequani from National Semiconductor, and our objective today is to highlight the history and the contribution that National Semiconductor made to the industry, microprocessor industry. On my left here is Dr. Giora Yaron. He managed engineering from his perch in Tel Aviv. On my right is Bob Freund, and Bob Freund managed the systems and software group for the 32,000 during this era. On my far right is Subash. Subash handled marketing for us at National Semiconductor for the 32,000 at that time. And on my far left is Don Alpert, and Don Alpert was our architect for the Series 32,000 for a period of time. Okay, let's start the discussion with Bob. How did the 32,000 get started at National, Bob?
Well, I mean, those days the Valley was just bubbling in ideas on how to employ acres of silicon into higher function devices, and at the same time other business ideas were popping up all over the place. There was this kind of undercurrent going on about workstations, and workstations were what was whispered in the bars at places around the Valley. And
this was about when, 1979?
Well, yeah, it was, yeah, 79, 80, in that neighborhood. And our Vice President of Technology, Pierre Lamond, I think always had the idea that the thing to do to help National move forward was to move it in the area of developing workstations. They built a workstation group, and they needed an engine for this workstation. At that time, the gold standard of architectures was the VAX. In fact, we had one. We used for all kinds of things. You used running Unix at that time. You needed one effectively to use it effectively in a group. So the architecture of 30,000 looks a lot like a VAX, kind of resembles it in some ways. Very VAX-like, but that and also the fact that, I mean, all of the silicon guys in the Valley are in a club, you know, and if Gordon's doing it, you got to do it. I mean, so all of the semiconductor manufacturers are trying to do this thing that they variously refer to as a computer on a chip, and various instantiations of a computer on a chip were things like the 32,000. There was a project for a while of putting a 360 architecture on a chip. Other people were trying to put PDP-8s on a chip. There's lots of experimentation in this crucible here. And that experimentation finally yielded the designs that we see today in the marketplace. And the 32,000 was one of the options that future history could have rewarded with success, but it didn't. But it really was, from a software guy's perspective, the ideal chip. It was ideal because it didn't cause you to have to compromise your implementation due to the quirkiness of the underlying hardware.
Now that instruction set was a superset of the VAX, right?
Well, superset, subset. We got to the point where, you know, one of the specialties of mine was compiler design and optimization, and we had the chip architects were trying to stuff more features, better instructions into the chip, say, look, we can go do this on the chip. And the compilers guys are saying, what would we use it for? Because we're looking for very simple atomic things, which is kind of how the RISC argument ultimately, you know, went. But very small part of the instruction set was generated by compilers, probably because we just didn't understand how to. But it did have a superset in some ways. From a purist point of view, though, the fundamentals of it was that it was a simple 32-bit architecture. And simple is good. Simple is not denigrating it in any way. That simpleness gives it kind of a symmetry, which makes it very easy to do several things within code generation. Lack of symmetry starts special casing things.
Subash, you were around at that time. I mean, you two folks were the earliest at National. What are your thoughts about how this started?
So a bunch of things came together. National had done pretty well in the past in the microprocessor world, in the sense that it took fair share of the market, but the market itself wasn't necessarily very large. Products such as COPS, NSC 800, IMP series, BitSlice, PACE, these kinds of products. So it was clear that there was something to be had here if we carry on with our technology and come out with better architectures, because the next big thing was going to be microprocessor revolution. More and more it looked like that the equipment will be built around programmable products, and so microprocessor was the way to go. And since we did have a start in microprocessors, it was quite natural that we build a better family, something which was much more advanced than the other competitors were thinking of at the time. And then that, along with certain other factors that came together, such as the vision of our then Vice President of Technology, Pierre Lemon. He wanted National to be on the map with respect to the best architecture out there in the world. So this, and then along with that, came along a bunch of very, very sharp engineers, all trained in high technology and processors and so on in Israel. So it was easy to form that group and get going very quickly. The right talent, the right quality and quantity, the right vision, and enthusiasm of the executive staff of National, because that then allowed us to sort of get out of what was considered to be jelly bean products at that time. So all these factors came together at the same time, and that's how it got started.
So basically, what we had was sort of a history of programmable devices, if you will, and then the workstation effort that we had at National kind of put this in a systems perspective, and they drove, it sounds like, the spec and the applications for this product. Does that make sense, Bob?
Oh, yeah, certainly. I think that the architecture of the product really was driven from at least what the vision of workstations were at the time. It's a good thing we didn't have to depend, Semiconductor didn't have to depend on workstations for its entire growth afterwards, because since it's really such a small market in perspective today. But then it looked like a big plum to go after. But the other thing that was kind of it's a good and bad thing, but a good architecture, best architecture, in that we really carved out a lot of territory. We did several chips simultaneously, memory management units, clock drivers, the chip itself, floating point units, and that parallelism, that parallel effort was what you needed to fulfill this whole grand vision. But in some ways, I think that, although presented a very nice marketing image, was in and of itself a little problematic, as we'll see as we go on.
So, you know, we had a history of making micros. We basically had an application, and we had some talent in Israel. And I'd like to kind of get to you, Giora. How was that talent really structured, and how did you communicate? Because we had a group in Santa Clara, engineering group. We had a group in Israel. Could you give us a view on that?
Yeah, it was a little bit harder and more complicated than described by either Bob or Subash here, because the architecture was borrowed, so to speak, from the VEX world. The marketing guys thought that all Israelis are smart, and the reality was a little bit more complicated than that. We were really asked to put on a piece of silicon more transistors than as a company we've ever put together. We were asked to have a process that didn't exist within the company. We were asked to use design tools that were not suitable for the task ahead. And we were asked to validate that when it gets to the customer first time, it's going to be able to run Unix. And when you think about how many engineers we had and how many chips we were trying to design in parallel, I think that there's no company in the history that I know that was trying to do so many things with such a team without really having a history behind them or under their belt to demonstrate they're capable of doing it. So really the task was something like climbing a 90% wall, totally slippery, no place to grab something to climb with. And the only reason we eventually managed to pull everything together really goes back to the quality of the engineers that we were able to assemble. I think we had in the country the best team ever. I think that if you go and ask, even today, about the quality of the team that we had then, everyone, at least in the country, would admit that that was not an A team, but that was an A+++ team. But even that wasn't enough to get basically the silicon to work right out of the bat, first shot. And very frankly, you know, in our industry, you call it steppings. We were going through step A mask set, stepping B mask set, and once we finished the American alphabet, we moved to the Israeli alphabet to be able to get everything right. And even the alphabet wasn't enough, so we had stepping A1, 2, 3, 4, and I mean, it was an unbelievable task. I think that the only reason we eventually ended up being successful in fulfilling the mission was we were young, naive, inexperienced, which is really what makes the Silicon Valley today what it is. If all the engineers knew what slippery walls they're about to jump into and try and climb, they probably would never started the task. And we had that quality, very smart people, very energetic, very naive about the task. And that's what eventually allowed us to get to fulfill the mission. That was compounded by another difficulty, which is only today people are starting to appreciate it, which is walking across geographies. And I still remember, Dick, the 4 a.m., 3 a.m., Santa Clara time phone calls. And I'm kind of waiting until, you know, morning hours are going to get there, so you'll answer the phone. So every time I move it 1 hour earlier, and gee, you are there.
I really enjoyed that.
Sure. So, I mean, it was endless. And very frankly, I'm not sure that it would have ever worked if it wasn't the two of us being, maybe not necessarily me, but definitely you, or a good communication between us, because you didn't have all the tools that we have today to enhance communication. And I think a lot of it contributed to the success, the fact that we were able to communicate problems back and forth, and in fact ended up translating this geographic gap, which is a barrier, into something that would work for us. Because we would talk early in the morning, my time, before you'd go to sleep, and when you woke up, which was my early afternoon, we'd talk again. So we actually ended up getting this machine to fix bugs and work and develop and work through the problems. Very frankly, 24 hours around the clock. And we really needed more than 24 hours. If we had 48 hours in a day, I think we would have known how to use that as well. So we'll get back to how we ended up solving many of these problems. But if there's a message to those who are listening to this tape, it's good to be naive, it's good to be energetic, but you need early on some gray hair around you to assist you in sizing the mission and making sure that you are properly resourced to make it happen.
And it's also, we took on quite a task. You might elaborate on how we differentiated ourselves from, let's say, what was going on in the industry at that time. I mean, we had Intel who was working on a CPU. We had Motorola working on a CPU primarily, and the same with TI and the same with Dialog. And we decided to take on the world's first.
All of them combined.
Yeah, well, that plus the world's first demand page virtual memory, the first floating point, and interrupt, control unit. And so we had to make that whole chipset work at the proper frequencies.
It's a system.
And I think, to me, there was quite a bit of learnings because we were building computers and simulating those computers with the power of, with less power. I mean, we had big mainframes with 6 MIP capabilities, simulating computers that were maybe 5 to 10 MIPS at the time.
And as well as you know, meaning the methodology that we ended up developing to debug those systems have given birth to several companies, and one of which is Vericity, which ended up being acquired by Cadence. The roots of that technology basically came from National Semi. We obviously didn't want to move into the CAD-CAM tools area, so therefore we didn't have a problem with individuals that have worked with us, specifically in this case, a bright guy, the name of Yoav Hollander, to take this technology and eventually commercialize it for the benefit of the industry. But the tools that we've developed are today part of, yes, you run into a young engineer, for him it's a given. Of course we use Veracity tools, meaning they don't even think that it was ever possible to pull something like this together without those tools. So, and this is just one side effect because we're not focused on CAD tools. We're focused on something totally different.
Yeah.
So we just had to develop our own tools to make things happen.
Well, you know, and that, we'll get back to that because I think it's an important point to explore that a little bit more. But I'd like to hear from Don. You know, what's your view of how, you know, the 32,000 family stacked up against competition? What was your view?
Yeah, well, I think that the 80s, which is primarily the period that we're talking about, was just an incredible period of evolution and companies entering and exiting the marketplace. And I think in this regard, the 32,000, as Bob was saying, was kind of like best of class of the so-called complex instruction set computers, kind of learning from the VAX and those that came before and coming up with a very clean instruction set right about the time that the industry, or at least academia and then the industry, was in transition towards this so-called RISC or reduced instruction set computing, and then later the superscalar, having multiple instructions executing in parallel. And I think that actually technically and in terms of architecture, I think the completeness of the solution, including we talked about silicon, but also the system software, as well as following those trends in the industry to deliver the compatibility together with the performance that the silicon could provide. I think in that regard, technically, it was really quite an extraordinary story.
Okay, let's move to, you know, I'd like to get back to Subash and talk about the market environment. So here, you know, we talked about how, you know, how and why we developed 32,000. Talked about how we structured our engineering group and how it stacked up. Let's go back and what was the market environment really like in the 80s?
Okay, so one clearly was extremely high level of competition. The products like 8086, Z8000, for example, represented a class of products which are good, which are accepted, but people were looking for more. Because the problems that they saw that were going to come in the future were of a kind that necessarily could not have been solved properly with 8086 or Z8000 class of machines. So in that sense, people were looking for something that gave them freedom to grow, because this industry, sort of called, let's say, microcomputer or microprocessor-based computer industry, was in some shape there, but now about to explode. So there were different types of solutions being talked about. On the one hand, there were multi-user systems, Unix-based, for example. Then there were people talking about workstations. Companies like Sun, for example, were being formed. Then there were personal computer, early variety personal computers. They were not called PC at that time. Some people called it home computer or, you know, small computer of some kind. Osborne, for instance, was born. So the microcomputer industry was going in different directions. There were issues related to what types of buses to be used, whether it is VME or multibus or a variant of future variant of multibus, what have you. On the other hand, there were really, really successful architectures such as VAX that people loved and liked, and they wanted to see something that could be translated into microform. And essentially, in some ways, 32,000 got its inspiration, if you will, from VAX, which was proven to be a good architecture. And if you could translate that into something usable in a chip form, that was just great. So people were hungry for newer things. Yet it had to be cost effective, it had to be performance oriented, and needed different types of software, all the way from operating system to application software. So there was a lot of demand from many, many different sources looking for solutions. And it was a fun environment as a result of that. And competition, I remember, was very, very heavy. I distinctly remember that at one time, once we had announced our product family, and we were splashed all over the place. We were winning awards of different kinds in the media and so on, and people were acknowledging that this is a great...
PowerPoint awards?
Those included. So one award we got was for one of the ads that we were running at the time. So I mean, it was fun time. All kinds of things were going on. And I remember that the noise level had become so heavy that actually there were our competitors that were looking for me to come over. And as a matter of fact, our notable competitor, Intel, had offered me to come over and run the 386 program. It was kind of funny because here we were not even shipping anything really in quantity, yet these people are running scared that something big is about to happen, so let's steal this guy away. And to my embarrassment, I was asked by my managers that, so are you about to quit or what? So I was completely dumbfounded because I had not accepted the offer. So they said, well, there's an article in Rosen's, Rosen used to write a newsletter, and it was mentioned that something good must be happening to National's 32,000 family because Subash Pal, the marketing chief of the product family, decided not to quit and join Intel. So it was fun time. It was highly competitive, a lot of work on the engineering side, obviously. Folks in Israel and of course back home in Santa Clara were working very hard, but so were we. We were running around all over the world trying to sell our product and technology and winning accolades. That was important. Yet at the same time just hoping that these things come out and we actually deliver.
Little thing of execution.
Yeah, exactly. So it was fun, at the same time stress.
Bob, you want to add to that? Or?
Well, one of the things that I recall, because when you're doing the software and systems side of this thing, you're never, really in the spotlight in a semiconductor company. Because you're the guy that's in a way a supporting role. In a way, you also help push the broom behind the parade, which is one of the things that we used to do. But we always got to the point of having to deliver something in demonstration form, a demo board or a little system, no matter what the steppings actually behaved like. We had to make it work. Okay, so we managed to make these steppings at least look like they worked.
No, they did work.
Well, to some specification. So the question that was from a software perspective, we looked at performance and complexity of instructions. I mean, today we fake out a lot of computer systems because we have so many instructions per second behind us. We can emulate anything we need. So if it isn't there today, we can make it. Back then, we didn't have that luxury to do that. Every instruction per second counted. And at the time, some of the early processors weren't meeting their spec. And I recall hearing time after time after time at sales meetings we would go to, at rep meetings, he'd say, where's the 10 megahertz part? Where's the 10 megahertz part? Now I know this doesn't, and this takes down to a really overly simplistic view, all the challenges and difficulties that Giora and his crew were facing. But it really is kind of the one thing that can get you, the one thing is that they say you advertise this, you spec it, when are you going to deliver it? And that lack of delivery or the time frame of delivery might have changed things. Maybe if we had delivered initially to full spec, but on the other hand, we had too much to deliver. We were carrying pretty heavy load at that time.
Giora, did we have too much to deliver?
No kidding. But maybe just to complement what Subash said earlier about the competitive environment, and talking about companies stealing talent one from another, we ended up having in a period of less than 4 months, basically 6 engineers, top talent that we had, basically resigning. It was hard to see initially whether there's a pattern there, but one guy comes in and he resigns. Where are you going to? Can't tell you. A few days later, another guy from another discipline comes in, he's resigning. Where are you going to? Can't tell you. Well, at the end of the game, it became very clear that it was a mini raid that Intel did on our engineering talent. This gentleman included in the architecture side, but so Dan was from the architecture side, Gideon Yuval from the software side, Lev Lavi from the circuit side, Dror Avnon from the floating point side. 6 of them basically in 4 months resigned, which triggered a love letter to Andy Grove. 1 more, and we're basically gonna start suing. But there's a saying, at least in my country, that crime does not pay. And there's an interesting story there. You're all familiar with the major write-off that Intel had to do for $470-some million.
475 million.
What's the exact number?
475 million,
$475
according to the
million.
research that we did.
Okay, so $475 million, and it's a bug that statistically has a probability of 10 to the minus 28, 9?
24,000 years.
Whatever, 24,000 years.
Yeah.
Interestingly enough, the same bug was discovered in our product called Swordfish. And interestingly enough, it's the same engineer that worked for us, ended up working on the floating point for Intel. So one actually needs to ask himself, you have an event with a probability of, what did you say, 24,000 years?
Yeah.
2 remote locations around the globe, the probability for that, whatever that's going to end up being. But there's only one thing in common, and that's an engineer that worked for us, ended up working for Intel. So you want to talk about crime doesn't pay. Well, this is a good example of that, but going back to the more serious side, there was endless competition on talent because everyone was competing and trying to climb these very slippery walls. And it was really a question of who is going to be able to get it right before the other. We know the competition had their own problems. I know that Intel advertised some of their problems with 286 and getting it to work, et cetera, et cetera. When I analyze why we eventually failed, I think it's for 2 reasons. We had an option. We could have failed, we as a company, National Semi, because we had a strong business in analog, we had a strong business in logic. Intel just could not fail. If Intel fails with the microprocessor, that would be the end of Intel. Having an option to fail basically creates a situation where management does not give you enough resources to get things done, whereas at Intel, Andy Grove himself was part of a task force, 8 o'clock in the morning, would sit there, take notes, what are the resources that are required, assign the resources, and that was the end of it. So that was part of it. The other part of it, I'm not sure the 32,000 architecture or program was born in the right company, so to speak. The DNA of National Semi was high volume production, analog, digital, and the likes. The sales force didn't know how to sell our products. They didn't realize that they were selling computers, for God's sake. This is not, you're not coming with your bag, okay? Do you want this analog? Do you want this logic? You don't like this one? I'll give you this one. You're selling computers, for God's sake. You're selling software. We didn't have the right talent. We didn't have the right compensation scheme for these guys. Having a design-in on a computer is different than having a design-in on a Jelly Bean product. So it was really a combination of things. We obviously have contributed our share because we have not executed in a timely fashion as we originally thought we would be able to. But we, as a company, we had a safety net. It wasn't a must for us to succeed. I think that if it was a must for us to succeed as a company, we would have been able to cross this Rubicon and be successful at the end of it.
So what would you like to leave, Don, what would you like to leave an engineer with? What thoughts do you have for today's engineer that you would like to leave with them?
I didn't know we were going to, I didn't remember that I was going to be on the question list, but I think what I usually do, and it certainly applies in this case, you know, it was just a odd, rare set of circumstances that got me over to, you know, to National. I got in microprocessors because I couldn't get a job with mainframes in 1980 at Amdahl. I worked at Zilog, and then I was moving over to Israel and just happened to hook up with National, with Uri, and with Giora. And it was just other things going on in my life that led to those opportunities, and just take advantage of whatever comes along and make the most of it, what you learn and the people that you meet, and the rest of your career will take care of itself.
How about you, Giora?
Well, I'd say two things. Rule number one is before heading for a mission, try and in a proper fashion size the amount of resources that you have to allocate to execute the mission. Rule number one. Rule number two, once you have embarked the mission, never take no for an answer. And the number of times that we got into a brick wall, or what we thought at the time was a brick wall, endless number of times we got into that situation. We refused to take no for an answer, and one way or another we found a solution. As I mentioned before, it would have been in design methodology, in compiler technology, in verification technology, every aspect of the technology. We ran into a brick wall, we got no for an answer, we refused to get no for an answer, and eventually came up with a solution. So if there's a moral to the story for the younger generation, we're going to be fading out of history quickly, by the color of the hair at least, is that the name of the game is really to make the impossible into something that's possible. And I'd like to think that we might have maybe written a small chapter, if you will, in the history of the Silicon Valley, which is known for the amount of innovation. I think we've written a chapter in how do you run a global organization. You talk to people in Cisco today, everyone is talking about collaboration, meaning we collaborate without all those collaboration tools, just getting on the damn phone at 4 o'clock in the morning and starting to communicate. So all of those are really studying new chapters in new books. And I'd like to think that the younger generation will keep on writing similar chapters or even more advanced chapters, if you will.
Bob, what would you like to leave with that?
Well, I just want to point out that I got a lot done with that software group communicating with the Twix machine, but that was all teletype.
I haven't heard that word in a long time.
Right.
Yeah.
The Twix machine. But no, I think if you're young and you think you're smart, a good way of trying to figure out how smart you are is try to find a project which is just an impossible project, and try to make it happen anyway. I mean, independently that you know it's probably not going to happen. Independent of the fact that there's just a lot to invent. Independent of the fact that maybe the environment isn't quite right, or the tools aren't there, or it's certainly not going to be. If there's any element of comfort in the job, you know it's the wrong job. It's the best job for a young engineer is to do something impossible. And that's, I think, the thing that was true for me and for many of the other guys on my team.
Subash?
So secret sauce or killer application, those things are, of course, very important, innovation included in that. But I've come to believe that it's very important to distinguish very clearly between ultimate vision and what's practical to do today. Nothing wrong, as long as the secret sauce is present right from the beginning. That's the core. And around which you can build a lot of products. Don't go for everything all at once. It typically, I mean, if you win, that's great. But I don't think the world really moves that way. It's okay to do it in phases as long as you're ahead of the game. But do keep that secret sauce going. Also, I feel it's very important that whatever ideas you have in terms of implementation, what's going to be going out in the marketplace, you vet it out working with customers and have a team, a good team going with marketing guys, sales guys, whatever it takes for a particular situation. But translating your ideas into an actual thing should indeed be a function of working in the field. Vet it out. Otherwise, you may indeed end up doing something which is brilliant technically, but may not be useful.
I really have just one simple message, basically, from the 32,000 program, and that is that the best technology alone doesn't necessarily win. And that the young engineer today should really focus on, even when he's in the best technology, collaboration and what I call technical credibility backlog building for himself as he networks, around. So I think that's the way I'd like to leave it. Very good. I think you guys did a very good job, and I think we've communicated.
Great.
Thank you, Dick, for organizing.
Thank you.
Thank you for the opportunity.